Let us look at the types of capacitance sensors that we have. In this case, we have something called the grounded sensors and floating sensors. Grounded sensors have the particular excitation as follows. So you have a CDC core, which is given by the symbol here, which looks like an analog to digital converter code. Here, the analog component being the capacitance input. So the capacitance input is given, and the capacitance input is a single-ended grounded sensor here and a differential grounded sensor here. Right now, in this single-ended, whatever is the charge difference placed is given back at the input of the CDC for a single-ended, and the other end is kept floating or it is grounded. So that is called Cin plus. Each capacitance sensor is protected with a shield, and the reason for having this shield is to ensure that no charge or coupling capacitance gets involved into the actual system. Right? In a differential grounded sensor, you will have two capacitance sensors present, Cx and Cy, both which can get vary depending upon what is the input. And each one of them can be given to each of the inputs, positive and negative terminal inputs of the CDC core, represented by Cin plus and Cin minus. The shield of these two capacitance traces is protected such that your excitation voltage does not cause any coupling capacitance present for the grounded sensors. So how does the differential grounded sensor work? The differential grounded sensor will have two measurements happening. One, you will have Cx and Cy. Now Cx varies with you can observe two things here. One, each of the Cx and Cy will have a nominal capacitance which is common to both. Right? And along with that, there might be some sensing value which is present in there. So this can be called as Cx delta, and this can be called as delta Cy. Now, the presence of the differential grounded sensor, you can say, now if you want to find the difference between the two, you do Cx minus Cy. What happens is the delta or the C norm gets cancelled in both places, and what you're left with is the difference between the deltas of Cx and Cy. So any change in this one, which is the actual change, gets impacted here. So this, if you want to have an analogy, when you have a signal, voltage input signal, which has got a DC component and an AC component, you could treat this C norm to be equivalent, right? Equivalent to the DC component, which on subtraction gets removed or nullified. And what is left over are the AC components, right? Which can be utilized. So this is the advantage of having differential sensors, wherein if any noise comes into the system also, it gets attached to the DC component in the capacitance. So any noise or impact of the excitation value, any noise or present to the excitation gets generally associated with the C norm. Norm stands for nominal capacitance. So the C noise will go, major portion of will go into DC, and what will be left over or any AC related component or dynamic component might get added or subtract, and I will call this as delta C noise. And this delta C noise is given as the difference between the noise seen in the X sensor and the Y sensor. Right? So this is the impact of the capacitance sensors.